No.
I've started sharing.
Not yet.
Oh, I don't see it yet.
Okay, can you see this? I wrote an A.
No.
Now the
There's
screen.
only G
Yes.
on my screen.
Okay, now
Yes,
it appears.
yes, we can see it.
Okay, so A, the closure of A is usually denoted in real analysis is denoted by this symbol A bar, and you have already seen this. Then A bar, and then if you take the second time, it is nothing else but A bar. And if it is something like this, this is said to be A bar subset of B bar. Now this is often called the monotonicity property. As you can guess why, if A is a subset, so then A bar is a subset of B bar, so that's why monotonically increasing and so on. This is often called the idempotence property. And this is often called the extensional property. There are two more things. One is the closure of the empty set is the empty set, and the closure of the whole, we are speaking about the real line, so the closure of the real line is the real line itself. And another one is the closure of the union is union of the closures. Now, somehow from the extensional property we get hold of this, because this is not too much to a demand. If we have the extensional one, then you can see that R is, the closure of R would be bigger than R, but closure of R is a subset of R. So this property is not really that important. It follows from extensionality. This one is something which is special, and it is called the grounded property. Means if the ground, the smallest one, is preserved. And this one is called the Kuratowski property. But in general, if we have any such assignment, this is for subsets of reals. Similarly, for the subsets of complex numbers, we have also defined closure. If we have any such assignment, A going to A bar, so this, therefore we will come to it. So this is a special kind of a relation. Such things are always called closure operators. And ground, it's a grounded closure operator, means it satisfies 1, 2, 3 plus the smallest one is preserved. Kuratowski closure operator, it means this. So closure operator plus 5. Obviously every Kuratowski, we will see later on, every Kuratowski is always grounded. Now, strangely speaking, since you told us, if you look into the reflexive closure, so A is a subset of any, so it's a relation, and you're looking into reflexive closure, say. Obviously, the reflexive closure, you know, this is, this join the diagonal of X, sorry. So obviously, the extensionality is satisfied, right? Now, the reflexive closure of the reflexive closure. Well, this is going to be A reflexive from your formula? But this is again same as A reflexive. So the idempotence is also satisfied and monotonicity is also satisfied. Okay? So the reflexive closure is also another example of a closure operator. And you will see that the same thing holds for the symmetric closure, the transitive closure, and hence the equivalence closure. Okay. So, so far, for instance, you had only one example or two examples of closures, taking closures. So you see, it is not a domain of real analysis. You have it even in plain and simple sets, you have closure operations. So that was one of the reasons why I introduced this, and I would come back later on when I speak about closure operators. I would come back to this connection again. So these are quite interesting operations. It's a process. You will see that the major importance or stress is not on particular formulas but processes themselves and relationship between processes. But let's proceed and I'll come back to this. So today, since we would be doing, we would be doing is that we were disturbed last time by our strange Jitsi colleague. So what we would be doing is essentially this section 4.1.4 about equivalence relations, and I will introduce functions today. Now, see, equivalence relations, the first thing is, as already, that the equivalence relation is reflexive plus symmetric plus transitive. And what we have done so far is, suppose if we are given any relation, then there is the smallest equivalence relation generated by it, and it is nothing else. First you take the symmetric, you symmetrize it, you make it reflexive, and then take its transitive closure. So that's and that is actually the idea. Another mistake, I was doing R op. So that's essentially 4.18, that theorem 4.18, and it follows from whatever we have done so far. So there is only one thing that you should try to give complete that proof. But so now we suppose we start off with an equivalence relation.
Prof,
yes.
Before you continue,
yes.
In the notes, maybe it might be the same, but in the notes, the equivalence, the R equiv, the brackets close after RU, R union, R.
Yes. Yeah, you're correct. I did that. That's in fact also equal to the same. So
it's the same thing.
Yeah. So that is also a good observation that if you take the transitive, if you take a transitive relation and add and take its reflexive, so symmetric, so before I, so I should, so show that the, how do I say this? See, what is this saying? This part is saying that it is symmetric and transitive, right? This part is symmetric, the first part. The first part is symmetric and transitive. Symmetric from the inner one and the transitive from the transitive closure. So what I am trying to say, the reflexive, okay, why do I write it again? So show this equality. This equality. Actually, both are same. Yeah, so that's a nice thing. So it doesn't matter how you do it. Okay. Now let's come back to this equivalence relation. Let's look into a first typical examples. Obviously, if you take R to be the whole of this, it is an equivalence relation. That is the whole relation is an equivalence relation. It's reflexive, symmetric, transitive. There is nothing to check. But obviously you can see, since it is reflexive, this is not an equivalence relation. If X is non-empty. Okay? But you have this, the diagonal, the delta X. This is obviously an equivalence relation. Not only so, this is the smallest equivalence relation. Observe that you can interpret this like equality on X. Because you know that xy would be in delta X if and only if X is equal to y. Okay, so this you can, so although we said that equality is something which we are not going to question, but this gives us a faint hope of trying to capture or trying to see what equality itself is in an arbitrary set. Okay, but this is not it. The real part of the game is that this is it. So every equivalence relation is some kind of an equality. Okay, now what the hell, you will say, what is this equality? X is equal to X, that is it. What do you mean by some kind of an equality? Well, we will come to this interpretation very soon, but first let's see now a few things, so some notations. So I will denote by this to be the set of all y's from x such that x are y. So this means this is the set of all elements of x which are related to x by r. Okay? So obviously this is non-empty because the relation is symmetric. X is related to itself, so x belongs to this. Secondly, if y belongs to this, then it implies that x belongs to this. And just by replacing, so this is nothing else but symmetry. And this is nothing else but reflexivity. Now this number 2 obviously has, over here, just you can interchange x and y. So this is actually not only one-sided thing, this is both-sided. Okay? So this tells us x by r is equal to y by r. So we can make it stronger. So x by r, this set y by r, we speak of it as if it's some kind of a division. Okay, and we speak of it in this way. We say x by r, and another way to say x by r is the equivalence class of x given by r. But I often like to speak of it as x, the element x by r. So this is true if and only if x are y. Okay, so two elements are related if and only if they have the same equivalence classes. Okay, now let's see another thing. Suppose I take two equivalence classes and let us see what do I have here. Suppose if I have a z here. So this means that z is in this and z is in here. So this therefore means that z is related to x and z is related to y. See, it's both-sided as we have done so far. So from transitivity, it tells us that x is related to y. Okay? And then since x is related to y, what we saw just now, this tells us So you see what is this telling us? It is telling us that x by r, this is a subset of, so it's a picture something like this. So this was your set x. This is x by r. This is the element x. This is the element y, say. So this is your x by r. I'm writing the names in blue. This subset. This subset is y by r. So the picture is exactly like this. Why? It said that if these two subsets had a common element, the situation can never be like this. If it had a common element, then both of them are same. So what it is saying is you have these subsets which is kind of partitioning, it's dividing your whole set X. So your whole set X, the set X is divided, or let's say partitioned, by the equivalence classes. Do you get it? Questions? Any questions?
Not from me.
Okay.
Yeah?
I wanted to ask about the equivalence classes.
Yes.
What are they uses?
What is there? Use.
What are equivalence classes?
So equivalence class, say, so this is, for instance, as I have drawn over here, this one. Firstly, it is a subset of X. Okay? And this is the set of all those members of all X elements which are related to X. So let's take an example and then it will get clear. So let's take an example. Let's take the set Z of integers. Okay? Now I am saying, what is my equivalence relation? Such that x minus y is a multiple of 4. Okay? Obviously, if x minus x is a multiple of 4, that's true. So it's reflexive. If x minus y is a multiple of 4, then 4 minus x is a multiple of 4, so it's symmetric. If x minus y is a multiple of 4, y minus z is a multiple of 4. If you add them, if you add two multiples of 4, you get x minus z, which is also a multiple of 4. So it's transitive. So it's immediate. It's a equivalence relation. Now let's see. What is x by r? This is nothing else but y minus x is a multiple of 4. Let's expand. So this means there exists a k in z such that y is equal to 4k plus plus x. Okay? Agreed? Agreed?
Yes.
Okay, good. So now let's see so therefore what are the possible values of y? Y looks like x plus minus 4, x plus minus 8, x plus minus 12, and so on. Right? So for instance, 1 by r, this has 1, then it has 1 plus minus 4, so 5 and minus 3, 9 and minus 7, 13 and minus 11, and so on. So if you observe, 6 is not there. Okay? Also observe, this is same as 5 by r. Because what is 5 by r? By your description, as we have said, this would have 5, then it would have 1 and 9 from here, then it would have 13 and minus 3, okay, then it would have 17 and minus 5 minus 12 is minus. See, all of them are coming up, but in a different order though. You see, they are coming up. So 1 by r is same as 5 by r, it is same as minus 3 by r, and so on. And so on. So we can see that 1 by r, 5 by r, 3 by r, they are all there. But 6 by r and 1 by r are not the same. So the equivalence things which are related to 6, and not only they are not equal, but they don't have anything in common. See, that's also, suppose if you had something which is common to both. So I am running that same argument. So this means 6 minus z is a multiple of 4. Okay? This is a multiple of 4. This means z minus 1 is a multiple of 4. So this means that their sum, which is 6 minus 1, that is a multiple of 4. But that is not true. Okay? So therefore, if you had anything common, 6 and 1 would get related, which I know is not true. So therefore, there is nothing common between these two subsets. Okay? Now let's see. So now let's analyze this a little more. How many such subsets are there? So how many such? So herein comes your very old theorem, the remainder theorem comes to help. Take any x in Z. This says that there exists a unique Q and R in Z. R can take the values only this, such that x is 4q plus r. Q is the quotient and r is the remainder. Right? Okay?
Yes.
So in therefore, by our how we have defined x minus r, this is equal to 4q, implying x by r is nothing small r by r. So there are only 4 such things possible. So what are the only equivalence classes? This is the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, and the equivalence class of 3. We often say that what is this equivalence class? This is all the integers which have a remainder of 1 when divided by 4. So the integers which have a remainder of 1 when divided by 4. Similarly, what is 2 by r? Remainder of 2. So we know that we can only have, when you divide by 4, the remainder would be either 0, which means that it is actually divisible by 4, or it would have a remainder 1, or a remainder 2, or a remainder 3. And clubbing these numbers, which are of remainder 1, gives me this equivalence relation. Okay, and it's exactly, so the equivalence relation speaks to us. This particular equivalence relation speaks to us. So we say that 2 numbers are equivalent when they are divided by 4, they have the same remainder. So this is what this relation is speaking about. So same remainder on division by 4. So what is turning out therefore? This big bunch of integers is divided into 4 subsets. One is the equivalence class of 0. One is the equivalence class of 1. One is the equivalence class of 2, and the other is the equivalence class of 3. That's it. Okay? So that is what it is saying. You give me so the division by 4, or remainder, having the same remainder when dividing by 4, gives rise to 4 equivalence classes, to a partition, to a division of Z into 4 classes, into 4 subsets. Division or partition means any 2 such subdivision sets are disjoint. If you take the union of these subdivision sets, it gives us, so you see, saying this, it gives us the whole of Z. It tells us, this is another way of saying, any integer Z when divided by 4 would have a remainder of either 0, 1 or 2 or 3. So this classical statement that was given by the remainder theorem is rephrased in this way by saying that Z is therefore partitioned or divided into 4 subsets, which is mutually exclusive because they are mutually disjoint, and it is exhaustive. Why it is exhaustive? Because exhaustive means you take the union, you get back all of them. So any Z is in exactly one of them. So that is the whole story, over here at least, and that is what is going to come up. So in general, so this is the abstract formulation of this. See, division, same remainder, division by 4, There is nothing special about 4. Take any number k. It may be a prime, maybe whatever. And we have number theory deals with all these things. What happens when you divide by some given numbers, right? So all of these are special cases of this general study where I am saying you take any set X. The moment you give me an equivalence relation R on that set, you get a partition. I don't know now how many dividing sets are there, how many partitions have been there. That much I cannot say, but at least I have a partition. Partition means I have a collection of subsets, any two of which are disjoint, and any member of the set is in exactly one of those partitioning sets. Okay? So the equivalence relations, giving an equivalence relation gives me a partition. Is this clear?
Yes.
Charles?
Yes.
Yeah?
It's clear, Doc.
Okay.
Yeah, I can get you.
Okay. But now the fascinating part of the story is...
Doctor?
Yes.
It's Ayub here. Can we say that those partitions are all of equal size?
No, that all... Good, very good. In this case of division by 4, yes, we will see that they are of equal size. Why 4 for any number? Yes, it is. For in many cases, we will see that they are, but there are several cases which I shall show today. Partitions may not be of the same size. Okay? So, there is nothing that we can say about how big are these partitions, how small are they, whether are they, only we can say that it is a partition. Okay? That much can be said in this generality. To assert anything more, we would need something else, something more to say about it. Okay?
Thank you. Yes.
Now, the fascinating part of the story is that this is it. What do I mean by this? Well, the moment you give me a partition, I can give you an equivalence relation which produces that partition. So I am going to show that partitions, the notion of a partition is same thing as an equivalence relation. These two notions are the same thing. Now, what is a partition? So, given a set, a partition of X is a set of subsets of X. So that means, what is it? If I take a P from P, then P is actually a subset of X, okay? Such that the first one is, each one of them is non-empty. Number 2, if you take any two members, then either they are disjoint or they are same. So there can be no question of a partial overlap. Two such partitioning sets, they are either disjoint or they are same. And the third one is union of P. This is X. Obviously, I didn't define completely. So what is this set? Now see, very, very naturally we have entered a place where there is a notion of a union which is not finite, which may not be, there is, I don't know how many partitioning sets are there and so on. So I need to think about what was a union. Well, what is A union B? Well, I collect everything from the sets A and B. So X is a member of A union B even only if either X is a member of A or X is a member of B. Now think of it, start thinking of this in this way. I have a set, I have only two bags. That means I have a set which has only these two bags in it. Now if I think of a union of this new bag which has only these two sets A and B, what is the union of this? Well, it is those elements which belong to some of the elements in this bag. So that's exactly what is this. So we usually write it in fact in this way, union of P. So what is it? A big U and then followed by this set. What does this mean? There exists a P in P such that X belongs to P. Okay? So this is the definition. So union of P, another notation for this is this. Or some people also, or we'll also write it sometimes like this. What is this? This is the set of all those elements which are members of some P in P. Okay? So the idea is exactly the same. You have now a bigger bag, not only having bigger bag, this script P, this is often, I shall call this P, this one P as a script P. In fact, you will see that in LaTeX, for instance, this comes with this symbol mathcal P. So this is how you write it like it, and it means it's a Gothic script, so that's why in short we say script P. So script P is a set of subsets of X, and what is union of P? Well, I take script P is a set of subsets. I take all those members which are in some one of the members in script P. That's it. Okay? So now, I'll pause a little bit. So is this clear, right? So you have, if you want another picture, so you have another, say, so this is your script P, say, and its members are, its members are, again, several subsets. These are all subsets of X, so they have several members in them. This is the picture. This is some member X, this is some member Y, and so on. And what you are doing is union of P. So if this is the union of P, you have just taken all of this but opened these bags. So how do I do this? So let me try. You have, let me see if I can copy it here. I need a bigger, 1 minute. Let me see if I can try to reproduce it here. No, what I do is I draw this one first. So I draw this one first. Up. I draw this one first. Then I make, so there is another one here. But I want to make these things, I want to make these things lighter, but I want to highlight these things. So I want to take these elements. So this is some element X over here, as I say, and this is why I did this. This gray means I cannot see those boundaries, right? So as if I had certain boundaries telling me these subsets, and now these boundaries have been removed. So that's how I made this set of union. So do you get the idea? So an element over here, how do you get an element over here? Well, you can find one such boundary. So this element, for instance, you can find a boundary over here to which it belongs. Okay? All right?
Yes, sir.
So this is
Yes.
the kind of intuitive idea that I'm trying to say by when I'm saying about a union. So you had a set of sets. So having a set of sets means something like this. There were already certain boundaries because they were already contained in those small bags. And you have just emptied these bags in a bigger bag, and that's exactly your union. So that's the idea. All right?
So,
now,
doctor,
yeah.
the bigger bag, would that represent a set X,
Uh,
capital X?
In this case, yes. Number 3 says yes. But in general, when I'm speaking of an union P, there I should actually draw some sets which are in something like this also. Okay, so I'm not saying that they are disjoint. I can take any such. I can have any collection of subsets of any set of subsets, and I can speak of their union. So speaking of an union doesn't mean that they are like this, and union of P may not be whole of X. So X could be actually there could be some elements outside also. Okay?
Okay.
But when I'm speaking of a partition, yes, then I cannot have anything like this overlapping set. I cannot have this. That's what number 2 says. Any two partitioning sets. So we will call these small elements, these small bags, or P's in P, as partitioning sets. So P in P, that's the name. So it's called a partitioning set. In general, when this P, script P is not a partition, we'll say a script P set or an element of script P or something like that. So any two partitioning sets, firstly, every partitioning set is non-empty. So that's the first thing. Okay? It says any two partitioning sets, they are either same or they are disjoint. Okay? And this one is saying that if you take the union, it's all of X. That means any member of X belongs to some partitioning set. Okay? So this is what a partition is about. So now suppose we are given a partition. So suppose P is a partition. So we are actually entering to set theory. You will see that I will draw diagrams side by side, but this is a feature. You will slowly have to throw away these diagrams. So these formulas would start to speak to itself. So now let's see. So you have a partition. So what does it mean? As I said, you have your set X and you have a partition. So that's what I am drawing by this subdivisions. Okay? So now I will give you a relation on X which will actually determine this partition. Now how do I do it? First observe, for any set, for any element X, so I am writing the formula. For every member of X, there exists a unique partitioning set such that X is a member of P. So that is something. How do you show it? Now let's look into the picture. I pick any element. Okay. Well, I will have to pick anything from inside this. So I pick this element, say X. The moment I pick up this element, I know that I have picked up this partition. You see, this picture is what I want to bring up in terms of a formula. So that is the formula here, 1. I take any member from, so how do you read it? You take any member from X. For every member from X, there exists one and only one partitioning member from P, script P, such that X is a member of P. Okay. Now let's try and forget this diagram and try to prove this. So, X is a member of X, which I know is union of P. So this, by definition of the union, this means that there exists a P in P such that X is a member of P. So the collection of partitioning members, partitioning sets which contain X is non-empty. But if P and Q be members of P and X is common to them, so you see this is where condition 3 I required. Then P is equal to Q. by condition 2. So, firstly, the first step shows that there exists a partitioning set which contains X, and the second one shows that such a partitioning set has to be unique, because you have told me any two partitioning sets is either disjoint or equal. Okay? So you are now sure. So you see this diagram, this picture which was brought up in this diagram is reflected in this formula. Clear? Yeah?
Yes, Doc.
Okay.
Yes, it's clear.
Now let's see. So now I'm going to define this relation. So define R. This is equal to X and Y such that there exists a P in P such that both X and Y are members of. See, I am using my. See, it's a kind of a cheating that I am doing. Why? How did I come up with this R? Come back. What happened? If I started off with an equivalence relation, I have this partition. And what are these partitioning sets? Well, if I have another element here, what are these? So this is the collection of all those things which are related by R to Y. This is the collection of all those which are related by R to X. So any two of them are related by R. Any two of them are related by R. So that's what I am doing. So partitions means they are related. So that's exactly what I am doing. So you have to do the most obvious thing. So what do? I take only pairs for which I can put them inside one partitioning set. That's what I did. Now let's see if I did it correct. Yes, by 1, R is reflexive. Because you take any X, you have a unique P which contains it. Therefore, XX belongs to P. Okay? That's number 1. So it's reflexive. Obviously, the way you told me, it is symmetric. Now, so suppose X and Y is related and Y and Z is related. So, it means that there exists a P and a Q in partitioning sets such that XY is in P and YZ is in Q. So this tells me that P intersection Q is non-empty because it contains Y. So this tells me P is equal to Q. So this tells me X is related to Z. So transitivity follows. And the final thing, I leave it to you to show. Just follow this relation. So what are all the relations? So, and 1. So what is X by R? This is precisely the set of all X such that X and Y are elements of a unique P. Okay? What is that unique P? Number 1 gives you, the moment you pick up an X, number 1 gives you that P. And then, so it is nothing else but it is P if X belongs to P. So X by R is this P. So therefore the partition which is the set of these equivalence relations, hence is exactly the set of equivalence relations, the set of equivalence classes of the elements of X. So that proves. So what does this show? This shows that equivalence relations and partitions are one and the same. Give me an equivalence relation, I will give you a partition of that set. Give me a partition, I will give you an equivalence relation which induces the given partition. Okay? So they are in one-to-one correspondence. I will not come to it, but you can understand now what I am trying to say by this. They are one and the same thing. But let's see another new way. So what does this tell us? Well, this tells us, so giving an equivalence relation means I have this partition. Okay? Now suppose I try to bring up a new set. What is that set? I try to bring up a new set whose elements are these equivalence classes. Which is the partition or whatever, and this is often called the factor set or the quotient set. Why? Let's see. Let's look into some examples. Let's come back to that example of Z and R. Here your Z by R is nothing else but this. It has 4 elements. We shall see later on that, we'll not see it today, but we'll see later on that you can still have a notion of an addition, multiplication of these 4 elements, and that is usually known as the modulo for arithmetic. Have you seen this? X equals to y mod 4, x prime is equal to y prime mod 4, so therefore x plus x prime is equal to y plus y prime mod 4, and so on and so forth. And this modulo 4, so things like this, we often write it like this: x is x prime mod 4, y is y prime mod 4. So this implies, say, xy plus x prime is equal to x prime y prime plus y prime mod 4. So we can as if do our usual arithmetic using these, but we can constantly go on writing it like this. Have you seen such problems or such things already? Any one of you? Am I still connected?
Yes.
Yeah.
Yes.
Yes.
Have you seen such
I
thing?
haven't seen.
Yeah?
I've seen this in group theory.
Yes, exactly. In groups. Yes. In numbers. This usually comes up as Z4. Right? so you see we have another set whose elements are, what we are doing is this equivalence classes. So as if I have factored, I have divided set the Z into 4 different elements, 4 different. So Z4 has only 4 different. But now you observe, what are you doing? You are 0 by R, if you actually see, when you are in Z4, it has 4 elements, 0 by R, 1 by R, 2 by R. But you see, 0 by R, it is actually a subset of Z which contains all the multiples of 4. So as if all the multiples of 4 have been glued together. Okay? So as if they have been glued together. All those integers which keep a remainder 1 have been glued together to give this equivalence class of 1. And same for the other two, right? So that's what I'm trying to say, that sometimes this is another version, another view of equivalence relations, we say of gluing. So all these elements here, they are glued together into one. They are glued together into one to give one of these. Then another is glued together into one. All of them are glued together into one to give another of them, and so on. Okay? So this is often the case. Here is a very nice way to motivate this. So, or in fact, such things appear in geometry quite often. Think of this square. Okay? Now what I do is this point, so I'm just trying to draw okay. So what I am trying to say is these points connected by these gray lines, the lines are not there. So that means this point is glued to this point. So A is glued to A prime, B is glued to B prime, and so on. Okay? So all the points on the top edge is glued to the point on the bottom, corresponding point on the bottom edge. You get it? What happens? Well, obviously, if you take a piece of paper and do this, what happens is obviously you will get something like this. One minute. So you'll get a cylinder. It didn't come. Oh. No, it's not making. What happened? Oh, this was not marked. Yeah. So now it would be easier. So let me see. So you would get something like this. And these two lines So this edge over here, this edge would become this kind of a circle. This edge would become this kind of a circle, and the rest is going to become continuous. There is no, yeah, okay. So you see, you can make a cylinder from here, and then, well, you can go further. For instance, you can go further. So the next step, for instance, is you can make what is called a torus or a donut from here. So you have this, and you have, so how do you get a donut? You then, it will be difficult for me to draw. I'm not a perfect artist. So these lines, so this point and this point, correspondingly this point and this point, you glue them again. So it's again actually another equivalence relation on the same thing, on this actually. So you have a further, so not only have you done this, actually you have done similar things on this on this horizontally also. So if you do it twice, what you get is a shape like how do I write? Yeah, you get a shape like a torus. I'll be really very at a loss to draw it. So it would be something like this. So, and then these are the circles. Yeah, these are the circles that we have taken. So, something like this. So, you see these geometrical shapes come up from just by specifying certain conditions, certain gluing patterns. Now, if you see, coming back to Ayub's question, so you can think of this as as say x is supposedly this 0, 1 cross 0, 1, this unit square. Okay. And what is your equivalence relation? Well, what is your partition? Your partitions are A, A. So this is one thing for A of the type. No. I should write it in this way. Say A. What is your partitioning set? Say A1 and A0. Okay. So this is your partitioning set. So P consists of sets like this. Plus, there is something more, because what about the interiors? AB, AB. So it's the singletons. Otherwise. Okay. So you see, the partitioning is having this and this. So this is your partitioning set, this and this. But for anything otherwise, this is the singleton. This point is singleton. You see, Ayub, that the partitioning sets do not have the same number of elements. Okay? When you do it, this gives another picture. So if this was your X and this was your partition, the corresponding equivalence relation is R. This is your factor set, which is now a cylinder. And then you have another way to describe this partition on this cylinder, and that gives you a further gluing, which gives you this torus. Okay, so it is again x by r, and if you go on actually writing like this, it would be something like this. But obviously we have to make some symbols, make it easy and so on. But so you see, so how do you get hold of a torus? You can get hold of it from this unit square by giving two equivalence relations. So this is a very, very common picture in geometrical studies where such shapes do come up, and they are actually split up or seen by, we say, declassifying the points, right? So if you declassify these from here to here, so you declassify means you cut it. You cut across here and then you can see this. Then you further cut along this, you can see this. So if you declassify it, you can get sometimes simpler shapes, simpler structures, analyzing which again you come back. So you see there is a process of gluing and declassifying. Okay? And there would be certain things which would be preserved by gluing, some things which will not be preserved by gluing. So you can see that we are trying to focus our attention on processes again, and certain processes which are preserving or maintaining certain kind of a structure. So you see, without actually ever specifying what a structure is, we can come up with the simple facet notion of a equivalence relation with such beautiful, fascinating structures like torus or cylinder from the square. Yeah. So that's the simplicity that is given by this study of equivalence relations and classification of such shapes. We'll come to more of this later on in later classes. And okay, I'll stop here. Now questions from you. Yeah?
Doctor?
Yes?
I've actually got a question that was, I typed it in the chat.
Oh, okay, let me see.
Some clarification, please.
Idempotence.
Yes. If Doctor can go up again to the page, I think 1.
Yeah.
So if you look at 2,
Yes.
the A double bar, is that equal to A bar or just A?
This side means you first take bar. Okay? That's
Yes.
also a subset.
Mm-hmm.
To which you apply your bar again. Okay? And the equation says that if you do this, you don't get anything more than a bar. What you already had it. Okay? So you can look at it in this way, as if to every, so what was we doing with closure? To every subset, we were assigning another subset called the closure of A. And these three properties then come up to say that, well, the closure of A was something bigger than A. Okay? And then if you take the closure of A and then further the closure of A bar, then you don't get anything more, but you just stop at A bar. So that is idempotence. So you apply this process twice, you don't get anything more. You get the same thing again. So that's why it's called idempotence. See,
okay.
The same thing happens if you take the union of a set with another set. You get something bigger. But then if you add that set again. So X union A is X union A. So the operation or process of taking union by A is idempotent. So it's much in that same feeling. It's idempotent. And you have seen already this idempotent law, which says A union A is equal to A, right? So it boils down to something simple also over here. We'll see that later. So it's idempotence of a certain operation. So it's the idempotence of this closure operation. Which says that if you take closure and then closure again, you don't get really something new. You still get closure. Yeah?
Thank you, Doctor.
If you look into the word idempotence, say in dict.org, if you are connected to the internet, you will see the word idempotence, for instance, or idempotent. Idempotence is completely a mathematical term. The term idempotent, immediately it says from mathematics, it's unchanged in value following a multiplication and so on. So it's immediately, it says it just came from mathematical usage. So it is not a English word also. So unchanged in value on performing an operation. So there it says by multiplication, but here, yeah. So it's the same thing. Yeah?
Thank you.
Next. Okay, if we don't have questions, then for the next week your submission will be for section 4.1.4 and up to up to the beginning of functions, that means up to section 5. Okay?
Dr. Gosh, do we submit via email?
Yeah, I think that is the best for now, because as I was explaining, submitting via which is the usual norm, submitting via my Unis platform. But since we changed our agreement on what we are going to assess, multiple submissions on my visa will not be accepted.
Right.
So it's better that we do it via email, and I'll maintain the record.
Thank you.
Yeah.
A question, Doc.
Yes. Before
4.1.
Thundakila asks
There's
me.
some special.
Please, 1 minute. Before so just to carry on with Rosella's query, since I will be keeping the record, and I'll also be letting you know at from next week's, let's say, your cumulative records. So it will be your kind of duty to tell me if I missed something and if something went wrong. Okay, because it is going to be manually done, so not automated one. So you have to tell me if things went wrong.
Thank you.
Yeah. Yes, Thandakila.
Yes, Doc. 4.1.
4 point?
A to I. Is that part of the exercise as well? Because I can see at the bottom there it says provide examples of relations of each kind. So is it part of the exercise as well?
Yes. Which where?
4.1. Definition 4.3. And then there's A to I reflexive up until total order.
Definition 4.3. 1 minute. Definition.
Page 13.
Page 13. Yes. Yes, I'm coming. Things have changed. What is the definition about? Yeah, this is definition 4. Yes, so
4 point.
it is
At the
about.
bottom, provide examples of relations of each kind. So does that mean it's all of that is part of the exercise as well?
Yes.
Oh, okay.
Yeah, there are how many? 9 kinds of relation. Yes, one simple way would be if you get out of wits with your usual say reals, complex, and blah blah blah. One simple, and see, we are working with sets, so you can make up a set with 5 elements, 4 elements, and come up with an example. That's it.
Okay.
Yeah.
Okay, thank you, Doc.
Yeah. Okay. Any other questions?